last but not least. So Changhun is going to talk about the latest classical algorithms for simulating the Gaussian boson sampling experiments.
Thank you very much for the introduction, and also thank you for coming back to attend my talk. Okay, so this I'm going to talk about our new classical algorithm that can simulate the largest Gaussian boson sampling experiment. So this is a joint work with Minzhao, Yuri, Bill, and Liang from Chicago. All right, so probably I don't have to really motivate too much on this, but I guess we have seen, like over the last few years, we have seen the first quantum advantage claims by experiment. The first one was by Google using random circuit sampling. And the second one was by USTC using boson sampling, more specifically Gaussian boson sampling. And our question was this: have we really achieved quantum advantage? And we focused on Gaussian boson sampling, as the title implies. And our answer is that, at least for Gaussian boson sampling, probably not yet. So I'm going to tell you why this is the case by giving you the overview of the experiment, the overview of the experiment, and also our classical algorithm. Okay, so let me first begin. Okay, so it's good time, like, because Scott's back. So I'm going to talk about the single photon boson sampling that was proposed by Scott and Alex Arkhipov. So let me first give you the short overview. The input state of this circuit is just n single photon state out of m input modes. So the rest of the input modes are occupied by 0 photons. So here, for technical reasons, we typically assume that the number of modes is much larger than the number of photons. So we can write down the input state informally in this way. So we have m non-negative integers where the first n integers are 1, which represent that the first n modes are occupied by single photons, and rest of them are 0 photon state. And so we are using this photon number basis. So we have m non-negative integers whose sum is exactly equal to large n, which is the input photon number we put. So this is the basis we are using. And of course, the dimension of the Hilbert space can be written in this way by simple counting. Okay, so and the dynamics of this input state is going to be a so-called M-mode beam splitter network, which is sometimes called linear optical devices. So what happens is that the photons going through this the bunch of beam splitter, and they interfere each other in the beam splitter. And we choose this, and also this beam splitter network can be represented by m unitary matrix, and we choose this unitary matrix to be H-random. And then after the dynamics, we measure the output state in the photon number basis. So we are going to get this m non-negative integers whose sum is again equal to large n, because we don't the number of photons is conserved in the circuit. And what makes it interesting is, of course, the hardness result in noiseless case. So the main observation was that the alpha probability of this single photon boson sampling circuit is described by the permanent of IID Gaussian matrix X. So I'm not going to go through all the equations, but the main observation was that the alpha probability is written as a permanent of Gaussian matrix X. Here, the permanent is counting the number of perfect matchings of bipartite graph. So using this fact, the hardness of the sampling has been proven under some conjectures. And it was a really nice proposal, but the problem in quantum optics experiment was that generating single photon is really, really hard. So it may not be a fundamental problem, but at least for the current technology, generating single photon is typically probabilistic. So that means that if you want to generate n single photons at the same time, then it would also take exponential time even for quantum devices. So you have to wait exponential time to generate n single photons because of this nature. So then what is an easier quantum state instead of the single photon state to scale up? Then if you ask this question to quantum optics people, then I think most of them would answer that it is Gaussian state. So then what is Gaussian state? Let me just use this one slide to define Gaussian state before I introduce Gaussian boson sampling. So Gaussian state, to define Gaussian state, let me begin with just elementary bosonic operators. So we have A dagger and A operators. which are called both photon creation and annihilation operators. Because we apply this to photon number basis, then we're going to destroy or create a single photon by 1 with some coefficient. And they follow this commutation relation. And if now we can define these two Hermitian operators, which is typically called position and momentum operator, X and P. And using these operators, now we can define what Gaussian state is. So Gaussian state are quantum state that can be fully characterized by the first and the second moment of these two operators. So if we know the mean vector and the covariance matrix with respect to these two Hermitian operators, then we can express any physical quantity you want using these expressions for this Gaussian state. So it's very easy tool to describe the state, especially for Gaussian state. So let me just give you like two most important Gaussian state examples in this talk. The first example is vacuum state. So vacuum state, you can easily check that the covariance matrix of vacuum state is equal to the identity matrix, and the first moment is equal to 0. So the vacuum state is 0 photon state. So it's going to be very important in this talk. And also another important state is so-called squeeze vacuum state. So as the name implies, what we have to do is to squeeze the vacuum state in the sense that we squeeze along this covariance matrix along a certain direction. So here I chose the direction to be momentum direction. So you can see that the variance of this of P operator has been reduced by this vector. And then but you have to increase the variance of the X operator because of the uncertainty principle. So here there's a free parameter R, which determines the squeezing, which is called squeezing parameter, which determines how much squeezed the state is. And one important property I'm going to use is that if you increase the squeezing parameter R, then the number of photon, the average photon number of your state is going to be increased. So when I say average photon number, because the squeeze vacuum state is no longer a photon number state, but this is a superposition of many different photon number states. So I'm going to talk about, when I talk about the photon number, I'm going to talk about the average photon number that is averaged over a superposition of many photon number states. Okay, so these are the important Gaussian state, but single photon state is not one of them. So that's why it hasn't been a very good state to realize the scale of the boson sampling experiment in experiment. So is there any questions so far? Okay, if not, let me introduce Gaussian boson sampling using this picture. So now we have instead of having this single photon input state, now we have an n squeeze vacuum state as an input, and then rest of them are still vacuum state. So using this covariance matrix formalism, what we can do is that the input state can be characterized by this m independent covariance matrices, where the first n squeezing parameter is equal to R because we squeezed, and the rest of them are vacuums, so squeezing parameter is equal to 0. So this is this is our state. And then the dynamics is same as before. We have a beam splitter network using Haar-random matrix. And the effect of this Haar-random, this unitary, this beam splitter in covariance matrix formalism is nothing but just rotating the covariance matrix. So you can just think of it as if you apply unitary on your circuit, then the covariance matrix rotates by some orthogonal matrix that depends on your unitary matrix U. So this is the dynamics in covariance matrix formalism. And then we measure in the same basis, at the photon number basis. So this is except for the input state, everything is same as before. And again, what's interesting in this circuit is, of course, the hardness result. So in this case, if you express your output probability, then what we can show is that the output probability is expressed by another matrix function, which is called Hafnian. So Hafnian is kind of a generalization of permanent in the sense that for permanent, we count a number of perfect matching of bipartite graph. But when you talk about Hafnian, now you don't have this bipartiteness constraint, but you just compute the number of perfect matchings of a general graph, so without any structure. So that, in that sense, Hafnian is kind of generalization of permanent. And in this paper, they also show that this output probability is expressed by Hafnian of XX transpose, where X is IID Gaussian matrix. So using the same logic, we have a hardness of Gaussian boson sampling under some conjecture. And the reason why we used Gaussian boson sampling instead of single photon boson sampling was to scale up. So this setup is now being used in this quantum advantage experiment. So any questions so far? Right. So okay. So I've been talking about this ideal case, but when we talk about these practical cases, then we of course have to consider noise. And this Gaussian boson sampling experiment, the dominant noise is called photon loss. That means that like literally, some of the incoming photons get lost in the circuit. So this effect is local. I'm going to describe what I mean by local very soon. So let's talk about the single mode input state as an input, and then how we describe photon loss in physics is that you have an incoming photons here, and then you introduce some fictitious beam splitter in the middle, so that some of the photons get reflected, so that they get lost in the environment. So we can't track them, and then rest of the photons just go through the beam splitter, so we get this as an output state. So this is kind of the description of this photon loss channel. And in particularly for Gaussian state formalism, it's very easy to describe its result. So if you have a covariance matrix phi of the input state rho, then the output state covariance matrix can be written as a convex sum of your input covariance matrix and the identity matrix, which is the covariance matrix of the vacuum state. And the weight of this convex sum is determined by the loss rate or a transmission rate equivalently. So here, 1 minus eta is going to be the loss rate in the circuit, in the channel. Okay, one useful property I'm going to use is that this photon loss channel does not change the Gaussianity of your state. What it means is that it transforms the Gaussian state into another Gaussian state. So we can just stick to this Gaussian state formalism. So what really happens in Gaussian boson sampling circuit is that this is ideal Gaussian boson sampling circuit I introduced. But in a real experiment, like this loss occurs really everywhere. Like when you prepare your input state, or when they go through beam splitter, or even when you measure, like this loss channel occurs really everywhere. The rate can be different depending on the position, but eventually loss is just really everywhere in experiment. So when I said local, what I meant is that this channel applies for each path. So it only occurs locally. And then I'm going to use very simplified number, which is overall loss rate, which is defined as basically the ratio of how much photons you get when you inject how much photon you put. Basically the ratio of the output and input photon number on average. And typical number in experiment is at least above 50%. So that means that in Gaussian boson sampling circuit, over than 50% of photons get lost when you in the circuit. And I want to emphasize that there are other types of noise as well, but loss is really the dominant noise in the current experiment. So that's why I'm going to focus on this photon loss only in this talk. All right, so now I've been talking about the effect of noise, but what's the real effect in complexity-wise in Gaussian boson sampling, more in general, in quantum circuit? So intuitively, we know that if we have an uncorrected noise in your circuit, then typically it transforms your quantum state to be a classical state that's easy to simulate, especially when you increase your system size. Let me give you one example that must be really familiar. So if we talk about this random circuit sampling, noisy random circuit sampling with a constant level of depolarizing noise per gate, then we know that because the depolarizing noise increases the entropy of your system, so eventually it will converge to the maximally mixed state as you increase the system size when your circuit has a sufficiently large depth. So in asymptotic regime, so the output state of noisy random circuit sampling can be approximated by maximally mixed state. That means that there is a trivial algorithm to simulate the noisy random circuit sampling, which is just sampling from uniform distribution. It works especially in the asymptotic regime. So when you scale up, then eventually you're going to get this maximally mixed state. Okay, the same logic actually applies in boson sampling case. So similarly, the output state of Gaussian boson sampling circuit with a constant level of photon loss per gate, per beam splitter in this case, and when we have a sufficiently large depth, then it's already well known that the output state converges to some classical state, which is called thermal state. I haven't introduced what thermal state means in this context yet, but you can just think of it as a kind of maximally mixed state in Gaussian boson sampling, in the sense that eventually, after a large amount of loss, it becomes a classical state that's easy to simulate. I'm going to revisit this part in the next few slides. So you can just treat this as some easy state easy to simulate. OK, so again, we have this trivial algorithm. You just sample from this thermal state, because as I promised, this is easy to classically simulate. But if you want to really simulate the current experiment, like finite size experiment, then of course this trivial algorithm may not work, because we are not in the asymptotic regime. So the output state of this noisy circuit, this lossy Gaussian boson sampling circuit, may not be sufficiently close to the thermal state. So if you just use the trivial algorithm, then you're going to have a lot of approximation error. So this may not be a good idea, and also the experimentalists specifically used some statistical tests to confirm that their output state is not sufficiently close to this classical state. And our contribution is this. So our contribution is that, motivated by this type of intuition, we invented a new classical algorithm that can take advantage of the effect of loss, so that we can reduce the complexity of our algorithm really much, so that we can simulate the largest Gaussian boson sampling circuit. Right? So then what is the largest Gaussian boson sampling experiment so far? So there are two different types of experiments. One is from Xanadu, and the other is from USTC. The details of the difference is not very important, but both experiments reported that they outputted over than 100 photons on average, which is quite large experiment in quantum optics. And the loss rate in the circuit was over 50%, so as I mentioned. So even though the loss rate was this high, but they still claimed that it would take at least 100 years, even if you use the largest supercomputer available now. So what is the basis of this quantum advantage claim? That is, of course, the best known classical algorithm at the time. And there are some more details about this best known classical algorithm, but essentially what's important is that you have to really just compute the output marginal probabilities one by one, and then you use this chain rule of this conditional probability. That means that you have to compute the output marginal probabilities, which typically cost exponential time as you increase the output photon number. So that was the main reason why the experimentalists tried to increase the output photon numbers, even though the loss rate was quite high.
Sorry,
yes.
But you said you come in with squeeze vacuum states. Does this complexity, how does this depend on the squeezing parameter R?
That's a good question. So one short answer is that typically we assume that we fix the squeezing parameter and increase the number of squeeze states, then it takes exponential time in the number of squeeze vacuum states. But if you just have a single squeeze vacuum state and you increase the squeezing parameter, then it doesn't change the complexity. So the number of squeeze state is the important parameter here. Yeah. Any other questions? So yeah, if not, so what I'm saying was that the best known classical algorithm, its cost increases exponentially in the output photon number. So that's why experimentalists focused on increasing the number of photons of their circuit without reducing the loss rate really significantly. But an obvious caveat of this estimate is 100 years is, of course, that this best known classical algorithm does not take advantage of the effect of loss much. So it may intuitively maybe quite an overestimate for this quantum advantage. So our contribution is to take advantage of this loss effect to reduce the complexity. All right, so I've been talking about the overview of the current status of Gaussian boson sampling experiment. Now let me really dive into our main results. So how do we really invented a classical algorithm to simulate the large-scale Gaussian boson sampling experiment? Let me first give you a high-level picture of our algorithm. So what we observed is that when you have a lossy Gaussian boson sampling circuit, then we proved that this circuit can be actually decomposed into two different circuits, two layers of the circuit. And I'm going to call the first layer as a hard layer and the second layer as easy layer. So the reason why I say the second layer is easy is that the second layer is just like essentially local operations, which cannot generate any entanglement. But the first layer is hard because the first layer looks just like a noiseless Gaussian boson sampling circuit. So that's hard part. And why is it ever advantageous? Why is the composition ever advantageous? The reason is that this, even though we have this hard part, which is noiseless Gaussian boson sampling circuit, but the number of photons of this new Gaussian boson sampling circuit is much, much smaller than the original Gaussian boson sampling circuit, especially the loss rate is really, really high. So that means that in using this decomposition, what we can observe is that this system has a very, very low entanglement because the number of photons is highly, highly limited. So that means that we have a very low entangled system. So we can use an obvious algorithm, which is a tensor network algorithm, such as matrix prostate. So to exploit this structure, so eventually using MPS, we can simulate the system. So let me talk about more details using this toy model first, before I talk about lossy Gaussian boson sampling first. Let me give you really a toy model here. So we have a single squeeze vacuum state as an input, and you have this loss channel. And as I explained, the output covariance matrix is written as a convex sum of this covariance matrix of input and the covariance matrix of the vacuum state. And then what we do is to sum them up, and then we decompose in a different way. So the second decomposition is no longer a convex sum, but this is the sum of two symmetric metrics, a positive semi-definite matrix. But there's some structure here. The first matrix looks like a covariance matrix of a squeeze vacuum state with squeezing parameter S. And the second matrix is a positive semi-definite matrix. So what we did is to show that the output covariance matrix can be written as the sum of two different covariance matrices. And if you have a sum of two covariance matrices, then what we can think of is a kind of a Gaussian convolution. What Gaussian convolution means here is that in just probability theory, just forget about this quantum circuit. So if you have a random variable x that follows covariance normal distribution with covariance matrix Vp, and then you perform a Gaussian convolution following the covariance matrix W, then you're going to get the random variable that follows a normal distribution with the sum of these two covariance matrices. So that's what I meant by Gaussian convolution here. And we can apply the same picture in quantum circuit, in this Gaussian circuit. So here, as I said, the first part, this Vp part, looks like a covariance matrix of squeeze vacuum state. So we just first prepare a squeeze vacuum state with squeezing parameter S. And then we perform a type of a Gaussian convolution in circuit. So when I say Gaussian convolution here, what I mean is that we already have this input state rho, and then we displace your quantum state by using this displacement operator. This action is basically just change your x and p operator by some constant determined by the input here, x and p. So we have this integral because we are taking the integral over this normal distribution of the random variable x and p following the covariance matrix W. So this above circuit can be written as in this form, and we can also further simplify in this way. You just generate a single squeeze vacuum state with squeezing parameter S, and then you apply this displacement operator with x and p following a random variable, the normal distribution with covariance matrix W. So what we did is when we have this lossy circuit, we can decompose this with a smaller squeeze state with some displacement operation. So one thing I want to emphasize here is that this decomposition may not be unique. You can decompose your positive semi-definite matrix into like in any ways. So you can find any other types of decomposition, but this choice is actually just one particular choice. But this non-uniqueness will be quite important in the next slide for generalization.
So what's the choice that you make and why?
Here.
Yes.
The choice we made is to minimize the number of photons from the first part. So we kind of minimize the number of photons here. So for a fixed circuit.
In the quantum part.
Yeah, quantum part. So yeah, I'm gonna read it there like in the general version. Right. So now let me really talk about the actual circuit. So as I said, that this is a typical experimental Gaussian boson sampling circuit. So we prepare a squeeze vacuum state and and they go through beam splitter, and there are a lot of loss in the circuit. But as I said, all the circuits are actually Gaussian, so you can just write down the output state using a covariance matrix V, which is a 2m by 2m positive matrix. And what we hope is to use the same decomposition as previous slide. So what I promised is this decomposition. The first, we have two different layers. The first layer looks like a noiseless Gaussian boson sampling circuit, and the second layer is kind of local operation. So I kind of assume one well-known fact in quantum optics that if you have a pure Gaussian state, that can always be decomposed into a Gaussian boson sampling type of circuit. So here I assume that the first layer has a pure state, so that we can always write down the first layer as a noiseless Gaussian boson sampling circuit. And then second layer is Gaussian and convolution that can be done using a local operation up to this randomness. So what we did is to just generate X and P vector following the covariance matrix W, and then we apply this random displacement operation following this random variable locally. So that you can see that the second layer is really local in this sense. Of course, this X vector and P vector can be correlated each other across the modes, but once you generate an operator, then the action is local. So that's what I meant by local. And as I emphasized, the choice of this VP matrix may not be unique. So we have to somehow choose a particular decomposition. But then what kind of decomposition we should choose? Our purpose is to simulate such a circuit. Then we want to minimize the computational cost to simulate this circuit. And as I said, the hard part is the first layer, and the easy part is second layer. Then what we want to do is to minimize some quantities of the first layer. And the choice we made is to minimize the photon number of the first layer. The main reason is that if you have a low photon number in your system, then the amount of entanglement you can have is limited. So that's why we choose to minimize the photon number of the first layer. And then I also used some well-known fact in quantum optics that the number of photons of your Gaussian state can be is proportional to the trace of the covariance matrix of your state. So to do this optimization, we make this program that we are going to minimize the trace of this covariance matrix VP for an input covariance matrix V. So here, the input of this program is this 2m by 2m covariance matrix, which corresponds to the output covariance matrix. And using this covariance matrix, now we are going to minimize the photon number of the first layer, which is trace of the covariance matrix, under some constraint. The first constraint is that the sum of these two covariance matrices has to be the original covariance matrix. And also, second constraint is that the W matrix has to be a positive semi-definite matrix because it has to be a proper Gaussian convolution. So it has to be a covariance matrix. We have a third constraint, which I haven't introduced, which corresponds to, it is also well known, but it's basically inequality to guarantee that the your state satisfies the uncertainty principle in quantum mechanics. So because this VP matrix will represent a quantum state, so VP has to satisfy the uncertainty principle. So that's another condition, another constraint we use. So we have this semi-definite programming, so we can efficiently optimize this circuit. And so this is what we use for decomposing the output of the experimental covariance matrix. And as a result, what we got is really surprising. So what we got is that after using this decomposition, we proved that we showed that the number of photons from the first layer, the hard layer, is only 3 to 7% of the overall output photon number. So that means that most of the photons were actually generated from this easy part that is only local. So that means that we have a really small number of photons for the first layer that can constitute entanglement. So what it means is that when you have a high loss, like the current experiment, then the output state will have a really small amount of entanglement in your system, as I mentioned. So that means that because the first layer is the hard part, then we need to just focus on simulating the first part, and then the rest of the part will be just kind of a trivial because they're local. So the idea is just to use the typical this matrix prostate method because the system has a really low entanglement. So we construct the MPS from the first layer and then just simulate the rest of the parts by just applying local operations. So this is algorithm overview of our our algorithm. So is there any question about this? Yes, please.
Yeah, you say like very small amount of entanglement. I think it was presented last year that was like 3%. Is that what you mean by small? That it's like 3% or something about that?
Yeah, this. Let me. You said like last year.
Yeah, I think it was last year. That it was maybe like 3% presented by Argonne. That like the.
Yeah, I think that's the same one. Yeah. Yes. So this ratio depends on the experiment, but typically the largest experiment between 3 and 7%. All right. So if there's no question, then I can now talk about this like thermostat again. So as I promised, so in the literature they have been already there is so-called thermostat approximation for Gaussian lossy Gaussian boson sampling circuit. So they didn't use our like picture because this decomposition is new, but we can interpret what they did using our picture. So after decomposing your output covariance matrix into this way, and then if you throw out the first layer, this hard part, which means that if you replace your Gaussian boson sampling circuit by a vacuum state, then that's actually equal to that's equivalent to this previously known thermostat approximation. So if you replace this by a vacuum state, then you can see that there is no entanglement at all in the system. So it's you can simulate this in polynomial time. So that's how the thermostat approximation works. But obviously, our algorithm is much better than that because now we are really like including more information from the first layer, like just instead of just throwing out all the information. So by using matrix prostate, we can approximate the first layer with a high accuracy. So that will result in a much better approximation accuracy. Okay, so using this algorithm, we eventually simulated the largest Gaussian boson sampling experiment. But one difficult part is like how to verify this again. So that's another like very important question. I think we have discussed a lot over this week. But let me just give you some overview, like how experimentalists verify their Gaussian boson sampling. So of course, the perturbation distance is a like theoretically good measure, but this is not very good in practice because this is not sample efficient and computationally efficient. So in Gaussian boson sampling community, they're using just computing many different physical quantities and compare if their experimental quantities are sufficiently close to the ideal score. But they also use this cross-entropy benchmarking inspired by random circuit sampling experiment. But one caveat in Gaussian boson sampling XCB is that we don't know the ideal score of the XCB. This is still open. So they still use this to compare with some other classical algorithms score, but this is not the way people use in RCS. So they just typically compute really many different quantities to confirm that their experiments are good enough. But even though they provided a lot of like benchmarks, but a few years ago, Google was able to spoof all the benchmarks Gaussian boson sampling experimentalists used to claim that advantage, except one particular method, which is called high-order correlation. So after this paper, this high-order correlation became really important verification method in Gaussian boson sampling community. And how Google was able to spoof all the benchmarks was that to invent a classical algorithm, that's a heuristic algorithm. And what they did was to compute local marginals. So here, like 2-point marginals only. So when you have an M mode, you choose all the pair of marginal modes and then compute all the marginal probabilities. And using this information, they made a heuristic greedy algorithm, classical algorithm, that can perfectly reproduce these local marginals, although they failed to reproduce high-order correlation. So this method was already enough to spoof many benchmarks, except for this high-order correlation method. So it has been the main focus on the current experiment. And our classical algorithm can can beat all the benchmarks, including this higher correlation. And I'm not going to list all the numerical results, but I'm going to just focus on this particular measure in the next slide. So what is this higher correlation function? So what we do is to choose k order like marginals. You choose k modes out of m modes, and then you compute this statistical like correlation measure. And then, so this is just one number. Then how do we make this as a like figure of merit to claim quantum advantage in experiment? So they typically use this so-called Spearman correlation, which is just one particular statistical measure to show that their outcome is close to the ideal outcome. So let me give you more how they actually compute this. So let's say we are considering case order correlation. Then we choose k marginal out of m modes. Then we are going to have m choose k different numbers. And then we compute for each choice. Then eventually we will have a m choose k number of vector. And then we compute this so-called Spearman correlation. And for ideal case, we compute by computing the marginal probability. And for experimental case, they use their samples so they compute this empirical higher correlation function. And then by computing this Spearman correlation function, if the score is 1, then they're perfectly correlated. And if there's 0, then they're not correlated. So this is between 0 and 1. And 1 means it's perfect. And this is the typical way of experimentalists do. And we also follow the same way because to see ours can win over this benchmark. So we also compute these ideal scores, and then instead of like using these experimental samples, we used our classical samples. And this is one result. This is the important result here. The x-axis is the order of this correlation. So here, if I say k equal to 3, then we are choosing 3 marginal modes. And then as I said, we now computed this Spearman correlation function, which is the y-axis. And you can see that up to like 5th order, our classical sampler score is better than the experimental score, which means that our this higher correlation function fits better to the ideal score than the experimental samples do. But like 6th order, you can see that it's almost 0. So it's hard to tell. Experimental one is slightly better, but they're still within the error bar. It's not very clear like which one is actually better. So up to the largest correlation we computed, and also what that was provided in experiment, we did not observe any clear advantage using all the benchmarks that experimentalists used to claim their quantum advantage. So basically, we win over all the benchmarks. And then what was the computational cost we used? So we used about 1 hour to simulate the largest scale experiment to generate like 10 million number of samples, like large number of samples. But we used quite a large number of GPUs. But this is not very large in the sense that typically this quantum advantage experiment compare with the largest supercomputer we have. With the 300 GPUs is like very small portion of the largest supercomputer's number of GPUs. So we used really a modest amount of computational cost, and it was already enough to simulate the Gaussian boson sampling experiment. So that's the main result. So let me conclude with this and with some open questions. So we invented a new classical algorithm that can simulate the state-of-the-art Gaussian boson sampling experiment. So this is one result, but the implication is probably more important. You can see that this is kind of this invention of new classical algorithm kind of guides the future experiment. So as I emphasized, all these experiments focused on increasing the number of photons to claim the quantum advantage based on the best known classical algorithm. But our new classical algorithm says that you have to really reduce the loss rate instead of just merely increasing the number of photons, because even if you increase the number of photons, if you don't control your loss rate, you might not get a better quantum advantage. So for example, what we showed is that, what we observed is that USTC did many different experiments, and the newest experiment, like last year, turns out to be easier than the previous experiment. Because although they detected more alpha photons than before, the problem was that when they increased the system size, they had to sacrifice their loss rate. So because the loss rate got increased, so our algorithm actually becomes easier to simulate the latest experiment. So it kind of highlights that how important it is to see like which direction you have to develop your experiment further and further to achieve a quantum advantage. Okay, finally, I'll just give you a few open questions here. One is that, like, an obvious question is there any better classical algorithm? So this is just one general question, but I have a very specific question on here, open question on here. So I emphasized that after decomposition, we have a really small amount of entanglement for the hard part. Then why does it take like 300 GPUs and 1 hour to simulate this? We can actually see that if you really wanted to just simulate the Gaussian boson sampling circuit with a covariance matrix VP without the second layer, it would have been really just instantaneous. So it's really small size of circuit. The problem is that we have to deal with the second layer. So to deal with the second layer, we have to store all the wave function, all the matrix product state of the first layer. That took quite a long time. So I personally believe that there is a much better, like much clever way than this matrix product state, but we couldn't come up with a better idea than using this tensor network. So I believe that there must be a better classical algorithm. And another open question is about verification. One is about this XEV in Gaussian boson sampling case. As I said, it's still open. That computing the ideal XEV score is still open in Gaussian boson sampling circuit. The main difficulty is to compute the second order of the second moment of the alpha probability. There have been quite a progress from a Maryland group by including Dominic, but I don't think we have a clear like analytical expression for the XEV yet. And also, I want to emphasize that XEV in GBS can actually be spoofed quite well, because marginal probability in Gaussian boson sampling has some information about the full output probability distribution. So it's not the case, but this is not the case in RCS. So there is some difference. So we don't know like what XEV means in GBS in a rigorous manner. And finally, so we are using many different like heuristic methods to verify the quantum advantage of Gaussian boson sampling circuit. So we need more efforts to invent a better benchmarking method based on the complexity theoretic ground. Yeah. Thank you very much.
I have one, if I understand you correctly, essentially only a few photons contribute to the complexity in this first part.
Yes.
Do you have from your numerics kind of a curve or so, you know, even if it's not analytical, of how this fraction of photons that actually contribute to the complexity depends on the loss rate?
You mean that as we scale up, right?
Yeah, I mean, if kind of understand like how much do you have produced this loss so that of your whatever 100 photons, 50 or so.
I have a plot prepared for that question, but like I don't want to go to too much details. But we can compute like how much bond dimension you are going to need to simulate if you scale up better. Like if you change the loss rate, if you increase the squeeze state, and if you increase the squeezing parameter, then you can kind of compute how much cost is going to cost using our algorithm. But I'm not gonna go too much of the details of this. But what I can say is the loss, like even though if you reduce the loss rate a little bit, but that doesn't really change too much. So you have to really significantly reduce the loss rate to increase the complexity.
Maybe I can comment on the second moment. It's true that we don't have an analytical formula, but we have a recursion that we can efficiently solve.
Oh, right, yeah.
I think for all practical purposes, you can compute the ideal XEV.
Okay, anyone else? Last chance. Okay, if not, let's thank Chung again.